Yeah, thanks for the invitation. Thanks to everyone who's here listening. I'm Matteo. As Sean said, I'm from Fondazione Bruno Kessler, a research institution in Trento, but I've also recently finished my master's degree in Aalto University in Helsinki, Finland. And so this paper is a collaboration between Aalto and SPK, where I work now. Thanks also to my co-authors. I see Nicola and Bintu here in the call. Nicola especially was my shared first author, so we worked on this paper together. So it's nice to see them here. So this paper talks about symbolic planning approaches, which is fundamentally a task where you have the current state of the world you're in, and then you have a certain goal you're trying to achieve. So for example, here we have these blocks in a specific configuration, and then the goal is to rearrange them so that they are in this other configuration. Or for example, in a simulated kitchen, a goal can be to put the bowl in the cabinet, et cetera, to wash the dishes. And then the goal of an agent in this sort of environment is to reach the end goal from the starting state through chaining together a sequence of actions that can bring them to the goal. And so this requires, in a certain way, like the ability to imagine what the world will look like after you execute these actions. So for example, if I move this block here, this blue block from here to here, I need to sort of understand what happens after I do this. And especially like thinking long term in order to solve these goals is something that is required for this. Typically, this is done using these symbolic planning approaches, particularly this PDDL or Planning Domain Definition Language is the standard abstraction for these types of problems. It works with symbolic predicates, which are Boolean statements about the world. So for example, you can see here, a predicate can be if an object is reachable or the agent is holding an object. And these can obviously be true or false, depending on what the world looks like at that time. And then we can use these predicates to combine and create these actions that can be chained together to reach the goal. And actions are themselves formed with two important sets of predicates. One is the preconditions, which is what needs to be true in the world in order to do this action. So for example, if I need to grasp something, my hand must be empty. And so the predicate empty hand must be true, for example. And then there is the effects, which is what happens after I execute the action in the world. So for example, in the same example of grasping, after I grasp, now the predicate object in hand will be true, for example. And so you can see that a symbolic planner, which is then basically a logic engine, can use these actions to do a search and then try to find a sequence of actions that satisfies an end goal, which is also defined in terms of Boolean predicates. This, however, can cause some issues or is not always easy to do because these predicates are true or false statements. But then, for example, we can do visual planning, which is when the input is an image. And so, for example, here, you would need to extract this Boolean predicate from the image somehow. So you would need to know that this robot is now holding the bowl, and then here it's not holding the bowl anymore. And it's not super trivial to extract them. Typically, this was done with end-to-end trained models, so like a CNN, let's say. But then this is not super scalable because you need, first of all, it's already labeled with this kind of predicates. And then these systems can only work on domains that are close to what they were trained on. They cannot really generalize to unseen objects or unseen environments very well. And so recently, the use of VLMs in order to do this sort of predicate extraction has come into view. This is a previous work that's called decay prompt. And what they did was basically query a VLM with this sort of yes or no questions, like is the cabinet open, is the cap in view of the agent, etc. And you can see that these basically correspond to one of these Boolean predicates I was talking about. So if you have an action you're trying to execute, you can use these type of framework to, first of all, if the action was possible to do, because you're checking the preconditions of the action. And then if the action was executed correctly afterwards, so you're checking the effects, because, for example, your agent might have accidentally knocked something over or like didn't grasp correctly the object you were trying to take. And so you also need to check if the action was actually done properly in the environment. And so VLMs can be used to do this precondition checking and basically extract the predicates from the visual state so that now you are living in this symbolic world, and then you can use your symbolic planners to generate a plan and then only use a VLM to check if the actions you're taking are actually correct. So this is a paradigm we call VLM as grounder. In the paper, we refer to this as evaluation settings. And this is kind of the loop I've already described. So you have an agent, you have a plan that's generated through a symbolic planner, which is a logic engine. And then the VLM is used to check if the action is executable and then if the action was successful. And if not, you can replan from the new state of the world extracted by the VLM using the same symbolic planner. But then there is another evaluation setting, which might be easier or simpler to set up, which is just use the VLM as a planner directly. So instead of asking the VLM to extract these symbolic predicates from the image, just simply ask what action should I take next in order to reach the goal. And so now you are free from the symbolic world. You are just using the VLM as a reasoner. And so you don't have these guarantees that the plan will be correct because you don't have a model specified in logic anymore. But on the other hand, you are much more free to explore, like the VLM doesn't really need this model to be specified by hand. And so it can work potentially in any environment that is it has never seen before. So our goal is to compare these two approaches and understand what VLMs can do and what they cannot do, which works best and in what scenario. And there is no real way to do this formally until now. So we propose this VPlan, which is a benchmark for visual planning with symbolic predicates and vision language models. So we hope to answer which are the best VLMs for planning and what is the best approach. Is it this VLM as grounder, which extracts visual predicates from the images, or is it using the VLMs as planners directly? And we may measure mainly the success rate in solving tasks, which is a slightly different metric from what benchmarks with VLMs use, which is accuracy. Here we just check if the goal was achieved at the end, not if the answers to the questions we were giving to the VLM are correct or not. We have two domains, which is blocks world and household. Blocks world is a classical planning problem where the goal is to rearrange these color blocks into different configurations. And then this household is a simulator where you need to solve various household tasks. For each domain, we have 25 problems over 3 difficulty levels so that we can have a fine-grained evaluation of how the VLMs are doing. We experimented with a lot of open source VLMs. Mainly open source, unfortunately, but we still had some budget to test GPT 4.1 and 4.1 Nano. And we tested it on both domains, on both evaluation settings, planner and grounder, and then with and without a chain of thought to see if that had any effect. These are the results. For now, these are without chain of thought. And you can see that on the blocks world domain, the VLM as grounder approach, so the one that extracts the visual predicates and then uses symbolic planner, works much better than the planner approach. The VLMs as planner cannot really solve the blocks world task very effectively. The two best performing models are GPT 4.1 and then Intern VL78B, which is a Chinese model. And then on the household environment, the opposite is actually true. So the planner approaches work very well, but then the grounder approaches cannot really solve the task. We speculate that this is because in blocks world, the task is much more formal. And so the VLMs cannot really use their common sense knowledge to know what to do. So, while in household, this is much easier because, for example, if I ask you how to cook an egg, you can probably understand that you need to find the egg, maybe it's in the fridge, and then take a pan and use it, even if the visual representation is not super clear. While in blocks world, moving the red block on top of the orange one, etc., doesn't really have any common sense implications. So the VLM cannot really guess what to do if it doesn't really understand what to do. On the other hand, extracting the symbolic predicates is very easy for the blocks world because it's just very clearly these color blocks. While in household, the environment can be more messy. There can be like the structures and objects around the place. And so maybe the extracting visual predicates can be harder. And so if you find yourself in a state, so if the VLM hallucinates and tells you you're in a state you're not really in, then it's really over. Like you cannot do an action, or you cannot predict correctly if an action can be executed or not. This is the leaderboard on the benchmark. You can see that the best approach overall is GPT 4.1 with chain of thought and with planner, so directly doing the actions. But then it's important to note that there is no strategy or model that outperforms the other ones. On blocks world, the best one is the grounder, as I just discussed, with chain of thought, and it's Intern VL, not even GPT 4. So Intern VL is outperforming GPT 4. But then for households, the best performing model is the planner without chain of thought. And you can see that there is a significant drop in performance here with and without chain of thought. This brings me to chain of thought again. And so we experimented with and without all experiments. And we basically saw that there was no real significant difference with and without chain of thought. Some models perform much better with chain of thought in a given scenario, but then, for example, fail completely in a different scenario where it should be equivalent, so in different environments. Some are worse overall. And then this, which I circled here, is the average of overall models. And you can see that there is barely any difference with and without chain of thought. And we even had some statistical significance tests and found that there is not really any significance. And we find that this is an interesting result. We have also read some other papers that say that the visual models or visual language models struggle to do chain of thought on images, that they work well on text, but when they are asked to reason about what they see in the image, this kind of collapses. And so this is an interesting piece of evidence to support this claim. Then an interesting point to mention is that there are, for the VLMS grounder approach, so the one that extracts these predicates, there are benchmarks that test something similar. So if I ask, for example, Pope, which is an object hallucination benchmark, the questions look like, is the object in the image, is there a dog, is there a cat, something like this. And these questions are very close to what we are asking. And these models are performing very well on these benchmarks. And so the natural question is why, if these models are doing very well on these types of benchmarks, then when they're asked to plan, sort of using the same questions, they fail. And what we find is that planning requires answering many, many questions sequentially in a row, all correctly, because as soon as you get one wrong, you hallucinate the state of the world, and then the plan collapses. And so here we sort of show that if you only had to answer one question, the accuracy of the models is very high. But then as they need to answer more and more and more correctly sequentially all at once, and they cannot do any mistakes, the performance drops very quickly as more and more questions are required. And the only models that can keep a decent level of performance are, again, GPT 4.1 and the interim VL. So in conclusion, we presented this benchmark for visual planning with two evaluation settings, VLMS Planner and VLMS Grounder, and then two domains, which is Bloxworld and Household. Both approaches we found have strengths and weaknesses. Particularly, Planner is better when the task is more common sense based, for example, in the Household one, while the Grounder approach is better where it requires more abstract logical reasoning, like in Bloxworld. We find that no VLM is really superior to all others. They all have sort of their niches. For example, Gemma by DeepMind is good at the planner, and this intern VL model is good at grounding. And then chain of thought prompting doesn't really help at all. Some future directions we are interested in pursuing is to extend this to videos. It's a natural extension. Now we are just giving the frames where the action starts and ends. In the videos, it would add an extra level of complexity because you also need to understand when an action is finished, because now time is continuous. Then we would like to introduce stronger evaluation settings, both for VLMS Planner and VLMS Grounder. Now we kind of kept them as simple as possible in order to have a fair comparison, but then we are designing this benchmark in order to be extensible so that people can bring their own strategies and evaluate them against the baselines, and hopefully we can form a more coherent benchmark. And then we also would like to reduce reliance on privilege information, particularly in the household environment and for VLMS Grounder. Since the environment is partially observable, we needed to give some information to the VLM beforehand, because, for example, if I ask if a cup is inside a cabinet and the cabinet is closed, the VLM has no way of answering, and so we had to give this information a priori. Yeah, thanks. And if there are any questions or if the discussion period later, we are happy to discuss. Thank you very much.
Thank you so much for the great presentation and talk. And I think the work is great contribution as well. We try to kind of keep the discussion to the end. So as you said,
Yeah.
so if it's all right, we can also move on to the second talk by Zhaowei. Zhaowei is originally from Hong Kong University of Science and Technology, but now he's staying in Edinburgh, as he told me earlier. And the talk will be on MMLongBench, benchmarking long context vision language models effectively and thoroughly. So yeah, this is another benchmark paper, and I'm looking forward to listening to your presentation.
Okay. Yeah, can you see the can you see my screen?
I see the
Okay.
yeah, the screen, yes.
Okay. Yes, thanks for the invitation, and thanks. I'm very excited to present our recent paper, MMLongBench benchmarking long context vision language model effectively and thoroughly. So I'm Zhaowei, and I'm from Hong Kong University of Science and Technology, and currently I'm a visiting student at the University of Edinburgh. Yeah, so the motivation of our work is that the current vision language models actually has longer and longer context lengths, like for the open source language models such as the InternVL series and VL models. Their context length grows from 8K to 32K, so out from 2K to 32K, and also the closed source models like GPT-4, GPT-4, Claude, and Gemini. They also have even longer context lengths, and so basically, we can say that current vision language models are long context vision language models, and there are a lot of applications of having those long context abilities of vision language models. Like we can have some long history of agents, like embodied agents, or also web agents or some GUI agents. And we also can have some very long documents here, like a document of 50 pages or even 100 pages. So basically, having those long context abilities are very important. But current limitation is that we don't have a very strong evaluation benchmark for the long context ability of current vision language model. So there are some limitations like the limited task coverage, like some data sets focus on the multimodal Neidoyan haystack or just the long context VQA. So those benchmarks only focus one type of tasks evaluating the long context ability of vision language model. And another limitation is that given the limited task formulation, the type of images covered is also limited. Like in the Neidoyan haystack dataset, they usually use some natural pictures, like the picture of a dog, a pet, a human, or some buildings. Yeah. And another yeah, that's the focus of the Neidoyan haystack dataset. And at the same time, there are some datasets that only focus on synthetic images, like some PDF or screenshot of the some apps. Yeah. And the third limitation here is the context length control. As we know, for the vision language model, we have both images and text in the input. So one fundamental challenge is that how do we count the number of tokens of images? So basically, previous work only used the number of images as the context length, but this method have some limitations, like different images have different sizes. So basically, if you put those images into the vision language model, they will produce different number of tokens, and those benchmarks also didn't count the tokens of text prompt or the questions. Yeah, so basically they will say that like this take this image as an example. They will say that we have 4 images here, and we have 10 images in total, something like that. But our motivation is that we need to do more fine-grained control of the number of tokens from images. Okay. Yeah. Yeah, and another type of context control is using the vision language model, like intern VL 1.5. Yeah, so basically you can also see that the context length control is also different between different data sets. Yeah, and yeah, and another the last problem is that the standard input length of the long context dataset. So previous dataset only use some random length of the dataset, like this takes a Neidoyan haystack this dataset as an example. They just concate some web pages to build a very long context. So the length of the whole benchmark, the whole example is actually randomly based on the length of each web page. Yeah, so our motivation is say that we need to control the context length at 8K, 16K, 32K, for example, to have some unified standard length of the multimodal input. Yeah. Yeah, so basically this is the design principle I just talked about. We have a very diverse task coverage, and we also have a unified cross-model token counting method, and we also have multiple standardized input lengths in our dataset. And this is overview of the comparison between our benchmark and other existing long context benchmark. Okay, so for the diverse task, we have basically five kinds of five categories of tasks, and in total we collected 16 data sets and more than 13,000 examples. Yeah, and yeah, that's so you can see that we have a lot of different types of tasks like visual RAG, needle in a haystack, many shorting, constant learning, summarization, and long document VQA. So those different kinds of tasks actually can cover different requirements of the long context ability. So for the next motivation, next strength is that we have a cross-model token counting for all the data sets in our benchmark. So here we for the text for counting the tokens in the text part of the input, we use the tokenizer of Llama 2 to count the number of text token. And for the image part here, we just follow the Queen VL series. We use 14 times 14 patches. And we also use pixel and shuffle here to reduce the number of image tokens. And this pixel and shuffle actually is commonly adopted in recent vision language models. Yeah, so and also for the standard length, we introduced 5 different standard lengths in our benchmark for each single example in our benchmark. Yeah. So here we have some detailed look of the tasks in our benchmark. The first one is the visual RAG problem here. So here we just use the knowledge-based visual VQA dataset, which is based on some question answering dataset in natural language, like natural QA, trivial QA, something like that. The difference is that we replace the entity here in the question with some image. So we use the image to represent the entity, and we retrieve some relevant passages from Wikipedia, and we ask the language model to answer the question based on the information from the Wikipedia. Yeah, and for the needle in a haystack here, we have 2 different data sets here. So first one is a visual haystack. So it's about finding an object in a haystack of natural images. Like this example here, we want to the vision language model to find this elephant and whether those and answer the question here whether those images have a dog. Yeah. And the second data set is about using the web pages to build a very long context. And here they proposed this needle in haystack data set proposed 3 kinds of task: retrieval, count, and reasoning. And we reorganized their input context to build the context length of standard length, like 128K input tokens. Yeah, and the third task in our benchmark is about the many-shotting context learning. So here we find 4 different data sets of entity recognition, and we ask the vision language model to learn the classification based on the in-context exemplars. So basically here, we replace all the class names with a random number from 0 to the number of the classes in the dataset. And we ask the vision language model to learn the mapping from the entity to the label number here. And then and we ask it to classify new images. Yeah, and the fourth task is the summarization here. So basically, we have a lot of daily documents that we want to read, but that are very long. So we here in this task, we just put the PDF formatted documents into the vision language model. We take the screenshot of the each page of the document, and we put those screenshot to vision language model to ask the vision language model to summarize the document based on the visual input. So, and we don't use any OCR tools to extract the text from those documents. Yeah. And similarly, the last task here is about the document VQA. So basically, we also use the screenshot of each PDF document, and we have some questions about those documents, like what does this table says, what does that figure says. see. Yeah. So here to control the context length, we also concatenate and or truncate some documents. Like a document is short, we randomly sample some irrelevant document to truncate a very long context. And if the document is very long, we truncate the document and keep the answer page to ensure that we have a standard length of the input. Yeah, and here is the overview of the images per example. So we can see that different tasks and datasets have different number of images of the input. So this basically saying that we have a very good coverage of the different kinds of tasks. And in our experiments here, we basically benchmarked 46 different vision language models, and we found that the Gemini 2.5 Pro is the best model here. And we also found that the open source for open source model, we also found that the models actually can generalize to longer context lengths. Like for Queen 2 VL and always 2, their pre-trained length is about 32K, and actually they can generalize to much longer, like 100 over 100K input. Yeah, and we also have some observation like the reasoning can improve the long context ability, and although the different model have different strengths on their favorite task. Yeah, so basically we also have some correlation between the tasks based on the performance of the model, and we found that basically those tasks have very low correlations, and we cannot just use the needle in a haystack to evaluate those vision language models, and we need to actually use a very comprehensive data set to evaluate the long context ability. And if we want to iterate the development of vision language models quickly, we can use the long document VQA here, because the correlation basically, its correlation is the highest. Yeah, okay. So basically, and I also give some error analysis here, but given the time limits, I will jump this part. Yeah, I also test some position embedding method like ER, and also some experiments. So we also include some experiments like loss in the middle in our paper. Yeah, so the conclusion here is that first we actually need a comprehensive benchmark to evaluate the long context ability of vision language model, and we also need such a benchmark to diagnose which part of the long context ability need to be improved of current vision language model. And here we also did we provide a very comprehensive and solid evaluation of 46 different models. And we hope that MMLongBench will serve as a standard yardstick for the community to benchmark the new long context vision language models. So, and that's all of my sharing.
Thank you so much for the great talk as well. And I feel like this is also another great contribution this session.